Alright, today we're going to be seeing how sound moves through the air around us. To understand this, we first must recognize the nature of the medium. Air is made up of gas molecules and has an elastic property. You can imagine the air as being springy. When the energy disturbs the air, it creates a wave that travels away from the source. This wave is known as a longitudinal wave. In a longitudinal wave, the air particles move in the exact same direction as the wave is traveling. Sound travels through the air in a manner similar to a row of upended dominoes falling over one after the other. The disturbance causes successive air particles to be moved in a knock on effect. This propagation creates alternating regions in the air, compressions and rarefactions. A half cycle of compression is followed by a balance in rarefaction, which causes a similar motion of particles in the opposite direction. These compressions, areas of positive pressure, and rarefactions, areas of negative pressure, form the wave. It is essential to understand that while the wave appears to move away from the source, individual air particles do not actually travel. Instead, they merely oscillate about a fixed point. The net result of this oscillation is the formation of a wave that travels through the medium. The amount of compression and rarefaction of the air is referred to as the amplitude of the sound wave. The distance between two adjacent peaks of compression or rarefaction as the wave travels is known as the wavelength. The speed at which this wave moves depends on the density and elasticity of the substance it passes through. In air, the speed of sound, usually denoted by c, is relatively slow compared with most solids. At normal room temperature, the speed is approximately 340 meters per second. Note that this speed is dependent on temperature. At freezing point, for example, the speed drops to just above 330 meters per second. For any sound wave traveling in the air, the wavelength and the frequency are related to the speed of the wave by a simple formula, c equals f lambda. This means that a fast traveling wave results in a greater distance between compression peaks, a longer wavelength, than a slow traveling wave, given a fixed frequency. A very low frequency sound of 20 Hz has a long wavelength of 17 meters, while a high frequency sound of 20 kHz has a short wavelength of just 1.7 centimeters. If any of this was at all interesting to you, I welcome you to keep following the channel and subscribe.